Okay, so at the end of the last video I said I'd show a live demo in this one, so that's what we're going to do right now. So just a quick glance at the code. This is what we're running. Obviously I've commented out the riskier method we're going to show that this does work for some boards. So yeah, the plan is it'll find a board it can't solve, it'll break on it, then I'll add in that code and I'll show that it can then solve it. So yeah, I think that's everything you need to know. Oh yeah, I've also like added in the default PyAutoGUI pause between move feature thing, so it's a little bit slower, but it's easier to read now and it looks a bit cooler. Just while it's doing this, we may as well talk about what my next plan is. So I plan on obviously doing like the brute force solution thing, and the way I've done that this first time is by using like recursion. Basically my plan is to have like you have an initial game state that you pass into some function, and what I want it to do is from that game state produce new potential game states below it, and then once it's produced those game states, it's going to check if any of those are solved or whatever, and then if they're not solved, use them to produce new game states, and basically we'll just get this huge tree and eventually it'll find a solution is the idea. You can see now it's got stuck, but the best solution that it found was okay, so it hasn't done very much, but it moved to here. Is that really it? Is that all it could do? Oh, it's moved orange as well. Orange went up here. So yeah, it couldn't do this level, right? So it got stuck here. Now, it might not seem that obvious that these should go on the edge, but it turns out that it is really likely. So what we're going to do is we'll just shut the code back up. So uncomment this right here. Save that. Bring the board back up. Just going to refresh the board. And now what I'm going to do is I'm just going on the code. I'm just going to break after we solve this level, so that we don't end up looping. Okay, so whoops. Flow free, yes, and you see now it's got a solution. So the reason it's got this, you see it's 5 times it hit the riskier method thing. So what I might do actually is if I go to you may as well be looking at the code with me. I might print out the board whenever we step inside here. So print unsolved board, and then what I might do as well is print the board again at the end. Print unsolved board right there. Actually, it shouldn't be at the end. It should be right here, I believe. So if we run this, now we should get loads of printouts of what the board is looking like at each stage, and it should help us to see what it's exactly doing. Okay, so whoops, didn't mean to do that. Which level were we on? No, it's 6 or something, I think. There we go, was that one, wasn't it? 8. Right, so when we start out, remember we got stuck here. This was the first time we got stuck. This is the board that it couldn't actually solve. When we go here, it's the exact same board, so it gets stuck with that board. It then uses riskier methods. Now this is the board it passed in, and the board it passed out was this one. So you see it's moved one more green move, so I'm just going to draw this board out as we go. So this is the board that got passed in. Now the board that got passed out was just one more green move. Now you can probably see this isn't actually going to help us because now we don't have any forced moves, so we're going to have to use another risky move. And basically if you follow this grid along, what actually ends up happening is this orange goes up one more, this green goes down one more, and now this green going down again. So basically we keep using these risky methods, and green gets to like so orange gets to here by the looks of it, and then green gets to green actually completes, green gets to here, and then this orange right here ends up coming out. Oh no, that's the salt board actually. So riskier methods don't get us that far. They get us to here. Okay, yeah. So we get to here, and now once we're at this point, we must have a forced move somewhere, do we? See, I can see forced moves that this red obviously has to go in here, but I don't think I've programmed that in. This was actually something I planned on talking about to add in. That's interesting. Maybe I have already coded that in, but I didn't think I had. Well, yeah, I must have programmed this in. So obviously, red must go into here, and therefore once red goes in here, okay. So I know what I've coded here. This is the group separation method that I've coded in. That's what solved this bit. So you can see this group right here, this 3 dead zone area. It only is connected to 2 ends of the red. There's only 1 orange end, 1 yellow end connected to it. So red must go in there. So that's how it solved this. It's not using this other method that I didn't talk about, but that I plan on talking about. So yeah, quite smart. It's actually solved the red, and then once the red's solved, obviously you can see that orange has to go around here, and now once orange goes here, blue goes down here, orange goes into here, blue goes into here, green obviously goes around here, and yellow obviously is there. So yeah, that one works. It doesn't use riskier methods that much. It's like 5 times or whatever. But some of the later methods, some of the later levels get like pretty ridiculous in how often they're having to call this riskier methods function, and obviously it can make mistakes. So we do end up with mistakes towards the end. So yeah, this video is going to be how we plan on getting rid of these mistakes. So I'm going to take a look at the code I've done elsewhere. This is the plan for a recursive method of solving this. You see, we import this script that we have up here, we import this module just so I can call all the other functions we've got. Basically the functions that read the board, basically all this stuff, reading the board and like transforming it into an array, stuff like that. I just didn't want to have to recode all them, there's no need when you've already done them. So the bulk of this boils down to this function right here, the recursive solve. So the idea is we're going to pass in the board. So we have a test up here that just has a board that I can edit so I can make it simpler and see that the runtime isn't too long. So it's going to pass in this board. You can see that this actually prints the answer of recursive solve with the board. So yeah, it takes in the board. Now we tell it what characters are ends, and it does a quick sweep over the board to check if any ends are connected to each other, and if they are, it'll connect them. This is basically the same function as the connect adjacent ends function right here. In fact, it might be identical. Yes, so what I could do, I could get rid of all this code and just call that function again. I didn't actually realise I'd already wrote that, or maybe I wrote them at different times. I don't know. Anyway, my point is this could be put into here instead. It's the exact same thing. This is actually a bit cleaner code as well. I wrote this a bit better than this. But yeah, that's not important. So this connects adjacent ends. Now, once the ends are connected, it says if this function here is solved and then board, if that returns true, jump inside here and return the board. This function checks if the board is solved. It checks if we have an actual solution. This is basically, if you've been following along, it's basically the same as the solved checker function, except it's a bit more advanced. This one here just checked if we had zeros in the board, so any board that was full counted as a solution, whereas this is solved actually checks is it a solution, not just is the board full. I'll go into this function in depth when we get there soon, but just for now, this just checks if there's a solution, see if we have a solution. If we do have a solution, we return the board, because the board is obviously the solution. If we don't have a solution, then what we do is we generate these possible moves. Now I'm going to go into this function as well, but for now what this does is it basically it takes in a board. So if we jump up with the game, I just want some simple level. I don't think we have any 3 colour levels, so we're going to have to take a 4 colour one, so let's just take this one. So what it does is it says here's the board, find the ends, and basically for each end how many possible moves can it make. So this blue one can only make one possible move. Now it says basically it takes in a board and it outputs all the possible boards that board could look like in one move time. So it could look like this board, it could also look like this board, it could also look like this board, it could look like this board, or it could look like this board, this board, this board, this board. You see how I'm going with this? So it's got all these different possibilities. So the like this, and then the yellow one could look like that. So it's got all them different possibilities. Now this function returns all of those as a list. So we iterate over the list and basically run this recursive solve on each board. We set the answer to temp because this recursive solve will either return the board or it's going to get to the very end of the function and not return anything. It'll return a none. If it returns a none, then we're not interested in it. We know we haven't found a solution yet, so we just need to continue. So if temp is not none, then we want to return temp because we know we've got a solution. Whereas temp in this case would be the board that it's returned. It's a little bit complicated down here and it took me like a long time to try and get working, but I'm pretty sure it now works and it's just about optimizing it. So if you read this code and you realise that I've made a stupid error where it could be improved, then let me know, but this does work for now. So yeah, it basically just recursively calls this function and this function until it finds a solution. Now we may as well go look at what this solved function does and what this find possible moves function does, and then we'll wrap this one up and I'll show you an example of it running on this the test board up here. So first up we'll look at this find possible moves function. Now this takes in the well, we tell it what the characters that are ends are. It has a list of boards, so this list of boards is going to be all the boards that the board you pass in could be in one move. Starts out empty because we don't know what it could look like. Now we sweep the board and we say if the square you're on is in the characters that are ends, so if we've got an end, then try this bit right here, also try this bit, also try this bit, and also try this bit. Basically these are all copies of each other, just with the indexes changed for the 4 different directions. What these do is it says if the slot to the right of you is empty, then that's a possible move. So we're going to add that to our list of boards. So list of boards dot append. We append like a copy of the board, basically slightly changed. Have a read of this. It's quite simple to follow. But then basically we just copy this 4 times for the 4 different directions, and then a really important bit that I've had to add is this bit right here, characters that are ends.remove. So basically, each time we find an end and we've checked its 4 possible directions for all its moves, we then basically say stop checking for that colour, because if you look at the board, we could say this blue can move to here, but also this blue can move here and this blue can move here. But now that's 3 different boards that this board could be, when really all we need to do is just look at one of the blues, because we could say this one can go here, and then this one can't move. We could treat this as like a static end, and basically only have to find from this end to the other end. So it's a lot simpler than having to go like, it could go here, but then the other one could go and meet it. But then there's also the possibility that this one could go here, and then this one could go meet it here. And then there's also the possibility that it could go here, and then it could meet it here. So you've got all these different possibilities that all get eliminated if you just treat one of the ends as static. So I don't know why I've not considered doing this before, but perhaps it didn't apply before. In fact, I don't think it did apply before. But yeah, basically we treat an end as static, and it cuts down on the number of like children that each board has. A child would be like a 1 generation time, like 1 move at a time board sort of thing. So yeah, it helps cut down on computation time massively, and it also helps fix like some weird bugs that I was having. So yeah, I'm sticking with that, and hopefully it makes sense as to why I'm doing that. Yeah, it does massively cut down on computation time, so definitely needs to be in there. Now, once we've got all these possible moves, obviously that gets returned and iterated over. So the last thing we need to check is this isSolved function. Now, this isn't too complicated, but it's got a little bit of like, you need to understand how the game works for this to make sense. So again, I'm just going to look at the board. Now, the rules of the game say that every isSolved is, right, back to the code. So isSolved is basically going to check if the board is solved. So I had to define the rules of the game, and basically this returns true unless it hits any of these conditions that will make it return false. So what we're going to do is we're going to take a look at what the conditions are for false. So how do we know this board right here that you're looking at isn't solved? Well, it's easy. There's loads of empty spaces. So condition number 1 right here. Okay, so first of all we take all the unique elements in the board. This just tells us what colours are in the board, and it also will take out the zeros. So condition number 1, if there's a 0 on the board, then return false. We haven't solved the board yet. So that one's really simple. Now, next we iterate over each colour, and we say the number of ends is equal to 0. Now, number of ends, so we'll go back to the board. Another condition for solving the game is that every colour must have 2 ends. So you might say this is an end, this right here, and this is an end. Now they are, but they're not technically an end. Not what I've counted as an end. What I've counted as an end is if you have a line like this, you now have 2 ends, because this one right here is connected to only one other of its colour, so it's an end point, and this one right here is connected to only one other of its own colour, so that's an end point. Now all the others on this line are connected to 2. Like this one right here is connected to this one and this one. This one's connected to this one and this one. So hopefully that makes sense. So every single line, every single colour on the board must have 2 ends, and only 2 ends. So the next check is number of ends equals 0. Now iterate over the board, check the number of ends it has basically, and if the number of ends, so the number of adjacent colours, no sorry, ignore this bit for now, we'll go over this in a sec. Basically once we've been through this, we know how many ends it's got. If the number of ends is not equal to 2, then return false. Every colour must have 2 ends. Now this other bit that I glanced over, this is checking the number of neighbours for each colour. So don't actually think I need this this line right here. I think just the 2 steps I've told you, if it is a filled board and every colour has 2 ends, then I think that's enough to check. But this bit right here just speeds it up a little bit. This basically says if we found a point on the board, like for example any of the dots right now, all of these, so in my code I define an adjacent colour as how many colours up, down, left or right of you are the same as you. If you have none the same as you, then you're like still a starting point, you're still a dot, you're still one of these dots like green right here or blue right here, and therefore the board can't be solved because you're not actually joined to anything. So that just sort of returns false immediately. That logic's not needed, that just helps speed up so we don't have to keep looping even though we found that it isn't solved. I could probably take that out and I don't think it would affect computation too much, but I may as well leave it, whatever. Now, last one is this number of neighbours. So this tells you how many of your colour are up, down, left or right of you. So it takes in the board and it takes in the position that you're interested in. And basically it says the number of neighbours equals 0. Now it copies basically this code right here 4 times for each of the 4 different directions, and it says basically if left of me is the same as me, then my number of neighbours is 1 plus 1. If above me or right of me, whatever, is the same as me, then number of neighbours plus equals 1. Hopefully you understand that. It's pretty simple. All encased in try and accepts because we're going to hit index errors at some point because of the plus 1s and minus 1s and whatnot. So yeah, that's where we're at right now. I'm just going to run this now for you on this board right here. So you can see I've partly completed this board. We have blue like partly completed, it's got to here, and then like partly completed up here and it's got to here, and basically just got to find this gap. And then red, green and yellow haven't been touched, they need to be fully completed. But you're going to see the problems with this recursive solver. So yeah, the problem is basically computation time. You can see it's still not solved. And by now, like the other methods that we've looked at in previous videos would have solved this. So this is why we aren't just brute forcing every board. This actually takes, I've already run this, it actually takes like 41 seconds to solve. And then I'm going to show you like a slight variation that you'll see in a sec. Whoops, here's the code running. I've been running it since you like heard me press enter on the video, so you haven't really missed anything. So just while that, oh there we go. So 45 seconds this time. Don't know what my computer was doing, but yeah, apparently it's 4 seconds slower now. So I'm just going to edit the code a little bit. I'm just going to fill in this blue line. So we've only really added like 3 changes to the board, but it now runs in 1 second. So you can see like the speed improvement, or rather the speed, like the slowdown, the complexity, as you need extra moves, goes up like at a ridiculous rate. Just adding in that extra 1 blue square made our time be like 40 times quicker. So you can imagine if I remove like the blue square we just had out, and then 1 more blue square, it's going to take like absolutely ages. So this just isn't feasible yet to solve boards. But what I plan on doing is adding in like a new check. So basically, right now as it is, the code, if I get rid of this, so in this recurse solve bit, if it's solved, it returns the board. If this function returns false, then it tries to find all the next possible moves and goes from there. But sometimes we have a board that isn't solved yet, but we also know can definitely not be solved. So for example, if we look at this right here, if green went up here, we know that board can now never be solved because blue's been isolated and blue cannot link with the other one. So a check for this could be using the what did I call it, like the group method. Blue now, so we could check the group, so the group would be like this black area, and we could say how many of the blue ends are you connected to. Well, it's only connected to one blue end, and none of the other groups, so this is the only other group, and this isn't connected to any blue end, so we can't solve blue. This knows that we can't solve blue. So that could be a check for it, and basically what we would do is before we so after we check if it's solved, but before we start finding possible moves and like recursing over this list, we would check, can it even be solved from this state? If it can be solved, then we generate all these possible moves and we recurse over them. If it can't be solved from that state, then we just hit a dead end, so just return none like we already do, and just move on, try a different board, like backtrack a little bit up the recursion that you've been doing. So my hope is that this will improve computation time a lot, and I plan on basically adding this in the next video, running it with the same boards that we've been running and just seeing what the time difference is, and hopefully I'm hoping with just a couple of like basic checks for the, so that this is going to be a like past constraints check. I'm hoping that with just a couple of methods added in there, we can get this down to like a reasonable time to solve the 5x5 by brute force. So yeah, that's going to be it for this video. It's been quite a long one. If you want to see the next one's probably going to be a bit more interesting. I'll be actually coding this stuff. I'll probably do it live on video. It shouldn't be too difficult, and then we'll run it a little bit live on video. So if you want to see that, stick around, check out the video that's going to be posted probably the day after this one. So yeah, subscribe if you want to see it, like the video if you liked it, leave a comment if you've got any suggestions. Like, I'm particularly looking for suggestions on how to incorporate all these methods I've laid out so far. So yeah, that's it for this one. Thanks for watching, I'll see you in the next video.